we want to, okay. So population versus sample. We are looking actually at measures of spread. So the last class we looked at central tendency. What's our middle number of the data? What's a good number to describe what they have? This is how alike or how different are the points in our data. And I'm just bringing up population versus sample because it's a little bit different how it's calculated. But first you have to know what that means. So a population, that's a well-defined group of objects about which to gain information. So here's some examples of population. The heights of middle school students in the United States. So the population there would be United States middle school students. If we want the ages of public school teachers in the United States, our population would be United States public school teacher, right? U.S. presidents is the population if I want to know which men have served there. It doesn't have to be people. Populations could be fish in a pond or something like that. It doesn't necessarily have to be people. So population. Often we can't get to an entire population. So we take a sample of members of that population. So it's a subset of the population. And it's very important how you choose your sample. Sometimes they're just randomly chosen. But sometimes you get a bias. And what does that mean? So let's say we're doing heights of middle school students in the United States. And my sample is I just look at Eagle Ridge. So that's right, because it's very hard. Can I get every single middle school student in the United States? That's a very difficult population to get 100% of. So if my sample is I'm just looking at Eagle Ridge, is that a good population to figure out, you know, with the entire United States? How about just this classroom? Why don't I just look at the heights of everybody in here? So is that a good way to figure out, well, if everybody here is around 5 feet, therefore the United States, everybody's 5 feet. Now what's wrong with that?
That there are adults and there are younger kids.
Well, we're just saying, yeah, well, we're just going to say like 7th, 8th grade. Well, yeah, we're just looking at a very small pool of people here. What if I just happen to have, by chance, a lot of extra short people? Let's just say by chance I've got little tiny people in here. Is that represented in the United States? Or maybe I've got really tall people, just by chance. So you have to be very careful how you choose your samples, and they have to be what we call representative of everybody. So maybe what you would do for something like this is you would send a questionnaire out to every middle school in the country and maybe get, 100 people from each. Would that be a better sample? Probably. Probably. So it's there to be very careful how you choose samples. But population, we could choose. I'm going to go back here just for a second. So let's say if I was doing middle school student heights, I would probably take a sample, right? I couldn't get everybody. What about if I wanted to look at just some research on how old public school teachers are in the United States? Would I be able to get the entire population? Or would I should probably do a sample? Yeah, it would be very hard to get every single person. And plus, don't forget, there's ethics involved. Some people may say, I want to be in your study. I want to do it. They don't have to. How about men who have served as U.S. president? Would I use a population as sample? Probably a population, unless, it depends what I'm asking. So I may not know some of the early presidents some of the information. So if I want something like their heights, I could probably do that with the population. If there was something about, I don't know, what might we not know about?
Their favorite color.
Their favorite color, right. If George Washington never wrote down his favorite color, it would be kind of a difficult thing to do. In that case, I'd probably use a sample. But, that would make this much less sense. But anyway, it's important. And the reason I bring it up is because we use different mathematical symbols and statistics, whether we're talking about a population or whether we're talking about a sample. So I'm actually going to go here with mean, because we've seen this one. Hang on. X bar. You don't get the difference between a sample and a population? A sample is just I'm taking a subset of the population. So if we wanted to know what's the height of every 12-year-old girl in the United States of America, I would probably just take a sample instead of every single one, because it's very, very difficult to get every single one. Now if I am working with a sample, that's when I use X bar to mean mean. Maybe another way to say that. So X bar, right? We're familiar with that? We talked about that last time. If I'm taking the mean of the entire population, I use this little guy here. Look at that. Look at that thing. It's Greek. It's actually a messed up M because this is pronounced mu, like a kid here. So mu. So we use mu to say find the mean of a population. We use x bar to say find the mean of a sample. Now, what's confusing is for us in this class only, we're not really going to differentiate between them. If you see an x bar and you see a mu, you're finding the mean. Your calculator will use this symbol. Most of our formulas, in fact, all of our formulas, will use this one. We're using population formulas instead of sample formulas, which are different. So that's a lot of way of saying, in our class, both of these things indicate mean. And what's a mean again? Add them all up, divide by the number you have, right. So both of these symbols, for us, in this class, interchangeable. If you go on with statistics past this class, they will have special meaning. And they just mean they're in different formulas. Okay, all right. Now, measures of spread, we've already looked at some of them. Remember range? Range is what the difference of the highest and the lowest, right? And it's a range of numbers. So if your test scores, your lowest score was a 60, and your highest score was a 90, what's your range of values? 30. How far apart? Right, they're 30 apart. An interquartile range, what's that? What's that one? Yeah.
Maybe like first one, the one quartile minus the double hand.
Upper quartile
In the highest quartile.
minus the lower quartile. What's that?
Interquartile is higher.
Well, it's the upper quartile minus the lower quartile. What is that?
Length of the box.
The length of the box. Exactly. So if you have a box of whisker, remember there's 5 things you find? That's the lower extreme. That's the upper extreme. The median's right in the middle. On your calculator, they call it Q1 and Q3. That's the lower quartile. That's the upper quartile. And that's where we make our box. So the interquartile range is this distance. I'll make my whiskers. And it says, remember, a quartile is just the median of an upper half of the median, or the median of that lower half. So you subtract those two to get the length of the box. So that's another measure of spread. Because if, as we recall, these are all 25%, right? So sometimes we really just want to know, how did our middle 50% work out? And so that's why interquartile range. What's the spread of our middle 50%? That's where that comes into play. Okay, so these are ones we definitely know this one. This one's a little bit new, but I think we can understand what that is. So now we're going to look at another measure of spread, and this measure is the average distance from the mean that you find in a set of data. Okay? It tells us how far from the middle, on average, each point in a data set is from the mean. You probably have no idea what I'm talking about. So let's look at an example. All right, so got a little family here, and they have 1, 2, 3, 4, 5 kids. 5 kids. So these are the ages of the children. Now, and you might remember last time I told you that there's a letter we use to represent number in a data set. Remember what that was? Remember? It's a letter. Yes, it's N. So N equals 5. In statistics, N always means the number of data points. So I'm just kind of bringing that back to the forefront. So I've got a data set where N is 5. I've got 5 pieces of data. And I want to know how far is each of them from the mean. It's going to be an indication of how spread apart or how alike the data is. So first of all, we have to find the mean. So let's find the mean. I'm going to get my calculator out. Because now, and remember, I want to use, and I'll just put that stat edit if you want to do this with me. It's kind of good to get that little finger memory in. So if you do this with me, what? Oh, let's put it in. Is it 14? Yeah. I'm looking for mean. 10, 11, 14, 15, 20. I do a stat, a 12, 1 bar stats, and my x bar or my mean. So notice it's going to say x bar in the calculator. I'm calling it mu is 14. Okay, how far away from the mean? So if you're 10 years old, how far away are you from that mean? -4 because you're under the mean by 2. Does that make sense? Now, how did I get there? I said 10 minus 14. So how, this 11-year-old, how far from the mean? -3, I heard it. Because that person is 11, he's 3 years from 14, so 11 minus 14, this says that person is 3 years under the mean. What about 14? 0, they're right at the mean. How about 15? 15-year-old, positive 1, right? Because that person is 1 above the mean. 20, 6, because 20 minus 14 is 6. So these are the values. These are the distances from the mean. So let's see if we can find the mean of these lengths. So I'm going to take -4, -3. Now I count 0, don't I? Yeah. It's how far from the mean. You can't just skip points because they're 0. So let's put that in the calculator, and we'll see what the average distance would be. So I put in -4, -3, 0, 1, and 6, and I do my stat, calc, find the other stats, and x bar is 0. So my mean, does that mean the average distance is 0 from the mean? Is everybody at the mean? No, it's like 4 people are not at the mean. So if I want to know on average how far away is everybody from the mean, I got a problem. Because these are the distances from the mean, and I take the average, I got 0. Well, what happens? I'm not sure what happened here. Let's look at kind of a table here. So if my mean here is where, it's 14. Here's my 10-year-old, 4 under, 11-year-old, 3 under, 14-year-old right there, 1 above, 6 above. Think about these distances here. This comes out to about 7, and this comes out to about 7, but this is negative, right? Think I cancel out?
Yes.
Is this always going to happen whenever I do something like this? Well, think about what a mean is. If that's the middle, then there should be an equal number below and an equal number above. So is this always going to happen if I try to average all the distances from the mean? And that's a yes. So that does not help me then. So the statisticians who kind of look at this stuff, because this is kind of an important number, I mean, maybe not in this situation, but it does say, on average, how far are they from that middle number. So what they did was they said, listen to this. Let's find a better way to find average distance from the mean. They said, and let's, we're using that word distance. Isn't distance positive? If you live 3 miles from the school, and maybe you live south of the school, are you going to say I'm minus 3 miles from the school? No. Distance is a positive number. It's a magnitude. So distance is always positive. So let's think about how we find positive. Absolute value. You guys remember this function? How does absolute value work?
You change the absolute value
From 0, right? It's how many hops from 0 is basically what it asks. So if you have like this number, absolute value of -4 is what? 4. And what's the absolute value of that? 4 hops away, 4 hops away, right? So the distance from 0 is what that finds. So we're going to use the absolute value so that we always get positives. So this distance from the mean, that's -4, let's make it positive. We're going to call that, it's 4 away. This one is 3 away. This one's 0 away, 1 away, 6 away. So if I find the means of this, 4, 3, 0, 1, and 6. So we can fix our, this thing here, let's make that 4, 3, and then stat, calc, 1 bar stats, 2.8. So the average distance from the mean is 4.8. So what is that tell us? 2.8, did I do the right thing? Oh, it's 2.8, you're right, sorry, thank you. It's 2.8. So what does that tell us? It's saying, see these ages? On average, these children are 2.8 from the mean. they're 2.8 from the mean. Yeah? Okay, hang on a second. Sorry for that interruption. So, on average, they're 2.8 away from 14. Okay, so what is that number trying to tell us? Let's see what happens. So the mean is 14. The average is approximately 3. 2.8 is approximately 3. So we interpret that to say, on average, each child is 3 years away from the mean age of 14, on average. Right? Some are closer, some are a little farther, on average. Now, let's say we have a blessed event. New baby.
0.
Now they've got, well, my N is now what? 6, right? 6 kids. So how old is a newborn baby in years? 0, right? So let's think about what this changes to our data. So what happens to our mean? Okay, so let's get our new mean in here. It's an eyeball. Oh, call the baby an eyeball. So let's see, 0, 10, 11, 14, 15. Okay, check it out. Put these in right. I think so. So my mean is going to change, right? So my mean is now 11.66666. Let's, for the sake of argument, I'm just going to call it 12 just to make this calculation a little bit easier. So now my mean is 12. What happened to my distances? So the new baby is 12 under the mean. The 10-year-old is now 2 under the mean. The 11-year-old is 1 under the mean. Now the 14-year-old is 2 above, 3 above, 8 above. So remember what we do is we take these absolute values. So I'm going to average these distances, RSI. Yeah? All right, we following? Yeah, if you're like, with your head in your hands and you're not watching, you're not going to get this. So with this, I'm thinking cap content. Thinking cap again. All right, so let's put this in. So 12, 2. What happened to the 14? It's not the median because we have a new baby who's 0. So I recalculated all those distances, and that's what I'm doing now. I'm averaging up the distances, and I'm getting about 4.7. Did I do that one right? Yeah, 4.7, am I right? I was wrong before.
Yeah.
Well, that's not the mean anymore. Right, they had a baby.
No, but on that way, what's the mean? Why is it
12.
What is the mean?
Because I have recalculated. I have the data. The old data, I didn't have a 0. My mean was 14. Then you add a 0 in here, my mean becomes 12. I just recalculated it all. And then I recalculated how far away from the mean. So now on average, we're more like 5 away. So my number, this 4.7, is now bigger than 2.8. So let's look at this. So before this baby was born, our mean age was 14, and on average, they were approximately 3 years away from the mean. After the baby, my mean is 12. On average, I'm about 5 years away. So what do these numbers tell us about the data? What do they tell us about the data that the mean does not? Look at this information. Without the 0, let's just get rid of this for a second. Are these numbers kind of close together?
Yeah.
Now once you put a 0 in there, are they still close together? No. Not as much. So what this number tells us is how close together are the numbers. A smaller number says they are closer together than a larger number. Okay? So the average distance from the mean, let's say we had quintuplets and they were all the same age. Poor person, 5 babies. They all made it to age 14, right? What's the mean of 14, 14, 14, 14?
14.
Let's think about average distance from the mean. What's the average distance from the mean for all of these?
14.
Yeah. So what's that averaged up? 0. So are these numbers identical? Yes. A very small average distance from the mean says that the numbers are very close together. The bigger the number gets, the farther they are apart. let's say we forgot, oh my goodness, we forgot about the kid that was like 47 years old. I don't know how this happens, medical miracle. But now, so what do you expect would happen to the average distance from the mean if this long lost kid of 47 was discovered? What's going to happen to this number? It's going to get bigger. So its variability is all about how alike or how different is the data. So these average distances from the mean tell us how alike or how far apart or how different the data is. That's what these numbers are. So I don't want to lose track of what they really are, because we're going to be doing calculations and this and that, and we forget what we're doing. We're looking for how alike are our data and how different are our data. That's what we're basically doing with the variability. Okay? So here's our conclusion. A small average distance from the mean means the data is close together. It's alike, or more alike, I should say. Small spread. A large average distance from the mean indicates that data is less alike, relative to each other. A larger spread. That's what we're looking at. Okay? So let's see if we can kind of apply this here. So I know the average distance from the mean for basketball teams. I got two basketball teams. One has an average distance from the mean of 5, meaning that they're all about 5 feet from the average height. The other team has an average distance from the mean of 10. So on average, they're 10 away from the mean. Which team has players that have more similar heights than the other? Now raise your hand if you think you know. Think about it, right? So one average distance from the mean is 5. So here's your mean. On average, they're about 5 away. And this one, on average, they're about 10 away. What do you think, Gigi? Right, so this is T1 and this is T2. You're saying T1. How come? So it's huge. Yeah.
And then there's a regular difference it's on T1, so this is and then there's 5.
Absolutely, this girl gets it. So what this is saying that on average, they're all much closer together than this wonky team with the 90-foot tall basketball player. Yeah.
I'm so confused about how do you get the distance from, like, what do you...
How do you get this number?
No, are you measuring from the median or the
Mean.
So on a normal line, like the mean in the middle? And
Yes. So this would be the mean right here, and this is how far apart. We're looking at actual, let's look at under inches because people do digits, right? So on average, they're 5 inches either above or below the mean, on average, all their players. And this one says on average, they're 10 inches above or below. So you're going to have a lot more, what we say, variability here. So I don't even know what the mean is. Do I have to know what the mean is to figure that out? I don't even need to know what the mean is to know which team has closer heights together than the other team. I mean, does that make sense? Yeah, kind of, right? We got to think about it a little bit. So questions about that. This is the big idea of the whole thing. Because we're going to be doing, type this in the calculator, do this, do that, do the other thing. But this is the important part. What are we actually finding? Whether the data is alike or whether the data is different. And we're quantifying that. We're assigning a number to it. Yes?
Is this bad?
Yes? Are you mad? What are you mad about? No. Okay. So yeah. Spoiling my game, the little punchline here. This, what we just found is called mean absolute deviation. So, right, we're working with the means. You know what that is. You have the numbers up, divide by the numbers you have. Absolute value is in there, right, because we had to take absolute value of distances. Deviation, this word, all it means is, remember we said take the age and subtract the mean? That's a deviation. How far above or below a mean are you in the units that you're working with? So you find it, you find the mean of the data, then find the distance from each point. And this here, next minus here, that's called a deviation. And take its absolute value, and then average those distances. So if you really understand what these words are, it says find deviations, okay, that's deviation. Take its absolute value of all of them, and then average all those numbers. That is mean absolute deviation. So we're going to practice finding it, This is a formula for it, and I put it in words. So x minus mu is my deviation. How far above or below the mean is the data point? So we take the absolute value of all deviations. Why do I take the absolute value again? What happens if I didn't take the absolute value of those distances? It gets to be 0, not helpful. So we take the absolute value, and you add all those up, and you divide by the number of points you have. Isn't that an average? Adding up points and dividing by the number that you have? So that is a special kind of average. Now, by convention, every point of data in a data set. So you know those kids, you had 0, you had 10-year-olds, 11-year-olds. We call it all x. This one's x, this one's x, this one's x. And then the mean is called mu, and n is the number of data points we have. So we're dividing by the number of data points we have. That's what you do when you find an average. And then we'll learn how to differentiate. Well, how do you know which x you mean if they're all called x? And we'll find that out soon. So add up all your absolute deviations, divide by the number that you have, you found mean absolute deviation. Anybody still with me? Anybody still with me?
Still with you?
If you're playing with a calculator, you're not with me. Okay, calculators are down. Put them down. Okay, so let's find the mean absolute deviation. Let's see, this is here someplace. Yeah, bottom of page 2. Okay, so S is the name of my data set. A set is a collection here, a collection of numbers. Curly brackets mean it's a set. 1, 3, 4, 6, 7, 9. I don't know what they are. They're not telling us what these data points are for. I'm not even asking you to find the mean. Because finding it is the thing that's going to be quick, right? You use the calculator, you plug in the numbers, it's 5. What does n equals 6 mean? How many data points I have? 1, 2, 3, 4, 5, 6. So I'm kind of looking at my formula here. So some of these things. So I need to find these guys. X minus mean. All right. So my mean is 5. Okay. So 1 minus 5, right? What's that? Negative 4. 1 minus 5. 3 minus 5. 4 minus 5.
Negative 1.
6 minus 5. 7 minus 5. 9 minus 5. All right, that's this part. Then it says, oh wait, you have to take the absolute values. Okay. So I have to find that because if I add them otherwise, I get 0. So this is absolute distances. Okay, now I average them. It says add them together, take their sum, and divide by the number that you have. All right, 4 plus 2 is 6, 1, 7, 8, 10, 14 over 6? Oh, let's see, 14 over 6, so 7 over 3, which is what? 2.3 approximately? So I'm just going to go with approximately 2.3. On average, the data points here are 2.3 away from the mean. Yeah, this is what the homework's going to be kind of doing. You're going to be finding these mean absolute deviations. So again, calculation-wise, that's how you do it. What does it mean? Now, what if I had another set of data, and I calculate the MAD, and it came out to 25 on another set? So what do I know about the numbers in this other data set? I haven't seen them, right? And versus this one. What is this number telling me? What's it telling me?
The numbers in the other data set are
Yes. So the numbers here are way different from each other than these. These ones are more alike than these ones. So I don't want you to lose the fact that what MAD is while you're doing all this calculator. I call it MAD calculator because that's what you do. So let's see if we can do another example here. So I'm on page 3. Okay. Wow, look at all this. So what are the steps? You're basically going to find the mean. Use your calculator to do this. Don't do this by hand. Finding the mean should not be a big labor-intensive thing. I'm clearing this out here. Put them in your list one. I got a 10, I got a 30. Look on your paper, it's easier than looking up. Putting in 60, 70. Typing in, everybody typing? I hear clicking, that's good. Where's that? Yeah. question, what's my N?
Separate rows.
So N is 14? What does that mean, right? 14 data points? One thing to check is, did you enter 14 numbers?
Yeah.
I did. And then check them. Please do not just say, okay, because if you make a mistake here, it's garbage. 230, garbage in, garbage out. So I'm doing a quick check. It takes a second. I make mistakes here all the time. I think I got it. So when you think you have it, go ahead and find the mean. Once you've got your data in and you check it. Okay, now you got a job to do, right? Here is 45 your mean. How do you find the distances? It's x minus mean absolute value. So what's 10 minus 45?
Negative
What's it gonna
35.
make it positive? Okay, so you have to do that for all of them. So I'm just doing x minus mean for all of them. You do the same. We'll see if we meet in the middle someplace.
We're making them up.
I'm finding the distances from the mean. Huh? I hope I'm doing
Why
it
are you
right.
doing all that?
Because that's how you find mean. You have to find x minus mean.
Oh.
So I'm doing that part. Absolute values. I'm doing this part right now. Right? I'm doing 45 minus 10 is negative 35. Take the absolute value. 45 minus 30 is 50. 45 minus 50. Okay? It's possible I made a mistake. You're going to take the mean of all these numbers.
How do you do it?
I hope I haven't messed it up. I'm going to put it in L2. How about that? Yeah, I'm going to put mine in L2. I put in 14.
Yeah,
I think I did.
Yeah, you just put one.
Uh-oh. That should be what, 15? It's hard, isn't it? Oh, just typing the numbers is so hard. You have to subtract. Okay, good question. Where did these come from? I see this x minus mean. So this is x. Or sorry, this is x, 10. Minus 45 is your mean. 10 minus 45 is negative 35. Take the absolute value, 35. 30 minus 45 is negative 15. Take the absolute value. 50 minus 45 is 5. 60 minus 45, I'm sure what that's supposed to be. Yeah? So you've subtracted. These are all the x's. This is x, this is x, this is x. They're all x. Alright, well let's see, I have to average them now, right? Now I've got mine in my L2. So I do a stat, I do a cal, 1 bar stats, I'm going to put it on L2, and I want that mean of 20. I got 20, what'd you guys get? Did you get 20?
I have 21.
Whoops. Well, it's 20, I think it's 20, I think that's the correct answer. So somewhere in there, there's a number that's slightly off. Wow! So that's the calculation for mean absolute deviation. Now, there is a shortcut. I don't know if I'm going to show you.
Oh, it's on my calculator.
What? Mean absolute deviation?
Yeah.
You must have a school note, because you don't have the other one. No, that's not it.
Oh.
That's just a coincidence. Yes. I don't know if I should show you this or not, but I'm going to show it to you. Here is, this is what I do. I never do all this by hand. So I'm going to clear out my L2. This calculator, if you don't get this, don't worry about it. This is not something you have to know. However, if you were to move up and see how my L2 is now lit, so you can get yours to do that and press enter. See my little cursors right here?
Yeah.
Okay, watch what I'm going to do. I'm going to actually program it in to find the absolute value of these numbers minus the mean. Okay. So first I have to do a stat calc one bar stats. I can't remember if I did that or not. So you have to do a stat calc one bar stats first. Then you do a stat edit. Move up one so L2 is lit. Hit enter. Press the map button. See the map button under the alpha button? Press that guy. You move one to the right so it says num. See absolute? Press it. Absolute value of what? Everything in list 1. I press second, then I press 1. Minus the mean. So if you know what the mean is, you can either type it in, or you go to this word bars. Alright, where's bars? See clear button? Look to the left. See bars? Press bars. Oh, just let me finish talking, okay? Here's number 5, statistics. We're doing statistics. Great. Here's number 2. These are variables holding what I just calculated. So now I'm taking the absolute value of L1, everything in list 1, minus the mean, and I'm pressing enter and look it up. It populates it with all those distances. Now that's a lot of steps. Do you have to know that?
Yes.
No. Do it by hand if you just had your brains explode.
I just had my brains
If
exploded.
your brains exploded, and I'll show you this again next time. But this is what I do because I make dumb mistakes. But anyway, and then you just find the meaning of this data like you did. All right. So again, just an OLP. So if you want to do this, you try, please do, and see if you can find first of all the mean.
Oh yeah, I did.
What's n? How do you find n? Right? 7. Just count them, and then see if you can repeat this process. So you can get. Some of you are still working, which is perfectly fine. But are we on the right path? We got a mean of 50.
Yeah.
We've got 7 data points.
Yeah.
As you're working these, are these looking like the correct distances?
Yep.
I mean, you may not finish this, but wherever you are right now, hopefully these are the numbers you're starting to see. Average these numbers. Take the mean. You should get 20. Mean absolute deviation is 20. Questions?
No questions.
So, summation notation is something important. And so I'm just going to do a real brief one. We'll review this again next time. You're going to be learning Greek. This thing here, I don't want you to look at that and see an E. It's not an E. This is a sigma. It's an S. It's an uppercase sigma. And when you see this in mathematics, it means add stuff. Summation, right? Sum is adding, so it's add stuff. How does that work? So you see a big sigma. Has anybody here ever done computer programming by any chance? Anybody? Everyone? Have you? You done some programming? Because if you have, most programs have something called a loop. And this is a loop. And it basically says, I've got a counter here. I start at the value 1, and I'm going to loop through, incrementing by 1. So I'm going to go 1, 2, 3, 4, 5. When I reach this value, I stop looping. Now, what am I doing when I'm looping? Whatever it says to do here. So this is kind of something saying, what are you adding? So what is this thing? It says, your I value when you start is 1, so this becomes 1. When I'm looping, because this is a summation, I put a plus. Then I loop back in, I becomes a 2. It bumps up by 1 each time. Then you look and say, gee, what am I doing? Oh, I'm just writing it down. Loop back in, put a plus. What's I the next time? 3. Keep going. Go back again. Go back again. And I stop when I becomes this value. So you're looping, looping, looping until you've done the last one. And this is what it wants you to add. So it's a shorthand way of saying add the first 5 numbers. And so what is that? 2, 6, 15? Right? It's a shorthand. Now, this may not look like shorthand if you're like, what? But we have to practice this because we're going to need this to understand the formulas that work with statistics. If you peek back at the first page, do you see these like sigmas kind of staring back at you? So part of the formula is understanding the sigma notation. I will do this a little bit more next time, but I just wanted to kind of introduce it here so that we have it a little bit on the brain for next time. Are there questions so far? Questions about summation, questions about math? It seems like an easy topic, awesome. Okay.